Swayam Prabha. Digital India. Educated India.
Welcome to lecture 30 of module 6, where we will discuss about different characterization techniques which are applied for knowing the surface quality of the surface as well as to know the degradation behavior of the surface. So, if you talk about the surface as we discussed earlier, so you are basically applying different techniques for improving the quality of the surface. For tailoring the surface, you apply different techniques, and before just application of the treated surface, or maybe before you just go on launching the product after surface treatment, you have to carry out several characterizations, and one of the important characterization is that characterization by non destructive testing, that is where from you get information about defect densities. But however, if you just think of the surface treatment or maybe surface coating, there are few important parameters which need to be understood, so that you can say that the component will behave well in the particular environment for which it was basically fabricated. Certainly, whether it will work or not, that actual testing you have to carry out by doing different mechanical and electrochemical testing as we discussed earlier, but otherwise before just doing those kind of destructive testing, you have to go for several characterizations, so that you know you can expect that the component surface will work well in that specific environment. So, if you quickly go through the surface parameters which need to be actually understood or which need to be characterized prior to do the actual testing, they are actually that, as I mentioned in the last class, that is surface defect density, then it is microstructure, composition and phase, texture, roughness. These all parameters need to be understood by you. So, now that for knowing these all things, it is very important that you go for structural observation. So, one of the important tool for which are used for, or maybe a series of tools which are used for structural observation is called microscope. So, if you just quickly go through the microscope, it is nothing but you just observe the surface at a higher magnification. So, one case you just visually observe the surface, and second case you do observe the same surface at a higher magnification. So, again depending on the magnification at which you observe the surface, you will see that you see different features on the surface. If the surface contains very small nano sized features, then you have to go to a very high magnification as high as 50,000 K. On the other hand, if you are interested to know very small features on the surface, you can see, if you are interested to know that immediately after processing how the topographical changes are there on the surface, then you have to go for observation of the surface at a very low magnification, and also you have to make sure that 3-dimensional features of the surface is visible. So, that is also one of the microscopes. So, you will see that there are series of microscopes which are available or which are used as tool for structural characterization of the surface. So, if you just quickly go through the history of different microscope, you will find that light microscope was launched in 1600, and then 1938 there was invention of transmission electron microscopy, people started using it. 1964 scanning electron microscope was there. In 1982 there was scanning tunneling microscope, which gives you information about the molecular features of the surface or atomic features of the surface. 1984 there was scanning near field optical microscope, and 1986 latest development is that atomic force microscope, and subsequent modification is the magnetic force, lateral force, chemical force. So, different forces are there. So, based on the composition like chemical species or based on the magnetic species, magnetic property change. So, there is also different types of atomic force microscope. So, quickly we will go through the different microscope a little bit in detail, so that you understand that how these different microscopes are useful to know the structural details of the component. So, first of its kind where you can observe the 3-dimensional features of the surface at a very low magnification, that is stereo microscope. So, stereo microscope is a very important type of microscope where directly you can see the what is happening on the surface. So, somewhere after processing you will find that surface is highly wavy in nature. So, if you just quickly remember the surface roughness, you will find that, remember the when surface roughness was discussed, you will understand that there are very small micro features on the surface which is called surface roughness. The surface again that this is actually the surface is not really flat in nature, it is the deviation from flatness is called waviness. So, actually there is waviness on the surface, and also that actual waviness, a waved surface is also not ideally smooth, there is roughness. There are also forms which is again nothing but the again deformation of the material from the surface. So, these all waviness or these all roughness comes from the prior treatment history of the component before launching the product. So, these all features need to be understood immediately after processing. So, certainly you can measure that by roughness testing unit, but those measurement gives you information about the smaller area. So, if you are interested to have the overall idea about the component surface as a whole, for example, component is having a dimension of 5 centimeter by 5 centimeter, may be irregular dimension or it may be complicated in shape, it may be flat in shape, whatever may be. If you are interested to know the structural features of this particular component immediately after processing, there what you do is that you keep it under this stereo microscope, and from there you get the average information of the surface. So, this is also called dissecting microscope. This typical feature of this microscope is that these are different parts of this particular microscope. So, you have that eyepieces, you have that typical objective lens, and you have stereo head, and sometimes you use LED light, that LED light to lighten the component, but actually component is seen in normal visible light. So, that is one of the basic features, you can see it under visible light, but you can also see it using LED light which is externally added on the in that particular microscope. So, here the feature is that you have two separate objectives are there, and two separate eyepieces are also there, and two separate optical paths are there, as a result of which you will find that in two different two eyes you will see two different features, and as a result of which you will get 3-dimensional image of the component, and by whenever you see it with the help of eyepiece. So, this is very important type of microscope, and which is usually everywhere in every lab, which gives you about the overall feature of the surface immediately after processing. Now, coming to the, if you are interested to know finer details of the sample, you have to take the help of the light microscope. So, light microscope is again quite very much popular and widely applied technique. So, initially it was very simple microscope where you had only objective lens, and with the help of a objective lens you just go on magnifying the image and see the image. But gradually there was development of compound microscopy where there are different lens combinations used to be there, objective lens and eyepieces, and from there you could magnify it further and see the finer details of the objective or final details of the component. So, basic features are that this is the different parts of the compound microscope where you have typical eyepiece, then objective, this is a objective turret. So, there are different objectives, then different objective turret. With the help of that you change the position of the objective, you have the objective lenses, you have to also the with the help of the you have coarse knob and fine knob. With the help of coarse knob, you just go on focusing in a coarse fashion, then you apply the, you just go on adjusting the finer these things, adjustment by application of fine focusing knob, and then there is a stage on which you keep the component, and there is a light source. Here with the help of light source you can, it may be that if it is light source may be downward position or it may be on upward position, and diaphragm and condensers are also there. So, with the help of that you can also go on changing the color actually, and then I mean light, you can use different filters, and then mechanical stages are also there. So, this is typical compound microscope. So, here before observing the component in compound microscope or by optical microscope, the mandatory criteria is that you have to polish the sample surface and then etch it properly. So, unlike to stereo microscopy, here you have to just go on polishing the surface by removal of the typical roughness which are existing on the surface, and then you have to, whenever we go on removal of the typical surface oxide layer or surface roughness, you have to follow several stages. Usually you go for you can go for mechanical polishing or you can go for chemical polishing techniques. So, in mechanical polishing you go on mounting the sample and then go for subsequently you do mechanical polish it using grinding different papers, which is nothing but called emery paper, where silicon carbide is embedded on the emery paper, and subsequently go on doing lapping. So, which is nothing but it is a kind of in a lapping wheel, where there is a kind of where there is a cloth, and on top of the cloth you go on sprinkling the alumina dispersed water or maybe any other hard particle diamond dispersed media, and subsequently you go on moving the keep the component surface fixed, but the disc actually moves, and there is polishing, and the polishing level is up to a level of 0.25 or 0.5 micron. So, whenever that polishing is achieved, then only light gets reflected from the surface. So, optical microscopy works on the principle of the reflection of the light from the surface if it is opaque material. Certainly, if it is transparent material as in biological species, it basically it depends on the transparency or transparent light, that the light is transmitted from the it should be light transparent. So, there is no need for any kind of polishing or anything, but particularly for opaque material, metallic materials, you have to polish the surface carefully. So, if you perfectly polish the surface, you will find that again light is reflected uniformly all throughout the surface. So, if it is reflected uniformly all throughout the surface, you will not really be able to observe the finer details of the surface. So, if you are interested to know finer details of the surface, so there is a process which is called etching. So, etching is applied, etchant is applied to etch the surface. So, etching is nothing but you just apply some chemicals which is highly reactive in a very small fashion at very slight chemical, you allow very slight reaction to occur on the surface. So, if you just quickly go through the polycrystalline materials, usually there are a lot of grain boundaries and grains, sometimes different phases are there. So, if you allow this particular surface to get reacted with the chemicals, you will find that grain boundaries basically they react in a faster fashion than that of grains. So, usually what happens is that you will find that grain boundaries and grains are quite distinct, and you will see that from the grain boundaries areas lights are basically that the lights are not really reflected properly, it is scattered. On the other hand, from the grain areas which is flat, therefrom light is reflected. So, from the change in these things, so wherever from the light is reflected, that is observed. So, grains are observed. On the other hand, where from the light is scattered, that region looks like black. So, you will find grain boundaries and grains very nicely using this particular optical microscopy, but you have to follow several steps, and these steps are quite lengthy, and also it is very difficult and you have to also remove certain layer from the surface. Obviously, you can also do that typical electropolishing prior to observation under microscope, where you just use electrolyte and then you just go on passing electrical current through that, you take the component as anode. So, whenever you go on passing that, just when you go on applying electrical voltage, you will find that initially there is increase in the current with the voltage, and at a particular threshold current it remains steady, and then it starts and then again when you just wait for longer period of time, there is overetching and hydrogen evolution. So, where it remains steady, that region is the typical electropolishing region or ideal region for electropolishing. You can also carry out electropolishing of the surface to know the finer details of the sample. So, whenever you talk about optical microscope, one important feature of the optical microscope is the numerical aperture of the objective lens. So, that is, it is nothing but how is the resolving power of the objectives of the microscope. It is given by the particular word numerical aperture. So, higher is the numerical aperture, more is the resolution of that particular microscope, or you can say that superior is the optical microscope, more superior is the optical microscope. Usually in optical microscope you cannot go beyond 1500 or 2000 magnification, and numerical aperture plays a very important role. So, if you just convert numerical aperture to that of resolution, you will see that resolution is nothing but equal to 0.61 into lambda is the wavelength of light which you are using for the observation of the surface, and divided by numerical aperture. So, higher is the numerical aperture, lower is the typical I mean you can say that higher is the resolution. Resolution means that this is R is nothing but it gives you information about the lowest the closest points which can be resolved by the microscope. So, lower is the R value, higher will be the resolving power of the particular microscope. So, for in one case your R value is 0.1 micron, other case it is 0.5 micron. So, you can say that which is having 0.1 micron R value, that is having higher resolving power than that of in the case where the R is having the value of 0.5 micron. So, these are the different stages of surface preparation which is followed during sample preparation under optical microscopy. Now, if you will see that one of the biggest problem associated with the optical microscopy is that surface has to be highly polished and reflective. So, this particular technique cannot be applied, optical microscopy cannot be applied for observation of the damaged surface. So, as we told you or as we discussed actually immediately after the damage like wear, corrosion, fatigue, these all surface dependent damage actually, we see that their typical features or their characteristics are only visible whenever you see under microscope, because you will find that unaided eye it is very difficult. For example, on the surface there are a lot of small pit formation. So, how the pit formations are there, it is very difficult to see unless and until you just go on doing microstructural observation. Similarly, if you say the case for wear testing or some failure due to wear actually, where you will find that on the surface there are a lot of scratch marks. So, deep scratch marks can be visible, but very low light scratch marks are not visible unless and until you do microstructural observation. So, microstructure plays a very important role to know the finer details of the damaged part. So, if you just go on, if you have the mandatory requirement of polishing of the surface after damage, certainly you will lose the damaged surface. So, by optical microscopy you cannot see these all features as is there on the surface because of the damage or because of the, you can say that because of certain damage whatever is there. So, if you are interested to know the damage mechanism, if you are interested to see the structure, you have no other option, but rather go for different types of microscopy, that is called scanning electron microscopy. So, scanning electron microscopy advantage is that it is having higher resolving power, much higher resolving power. Second advantage is that it does not require any kind of polishing, its depth of penetration is much higher. So, scanning electron microscopy is very widely applied for the observation of the damaged surface or for knowing the you can say that mechanism of the damage of the component. So, for fractographic observation, scanning electron microscopy is mostly applied, it is applied to a large extent in addition to that of stereo microscopy. And furthermore, if you are interested to know finer details of the surface after the surface is processed, then you have to go for no other option but scanning electron microscopy. So, if you see the working principle of scanning electron microscopy, you will find that here, as the name implies, it is electron microscopy. So, electrons are the component is subjected to irradiation with electrons, and scanning means you just go on the scanning electron on the surface, or you go on rastering electron beam of electron on the surface, and then subsequently you capture some with the help of the any detector, you capture the electrons like depending on the kind of information you are looking for, and find out the features of the component. So, for example, whenever the electron beam interacts with the surface, there are different phenomena which are shown here. There is generation of OJ electron, that is right from the near surface region. Then after that there is secondary electron emission, then below that there is backscattered electron emission, and then below that even there is characteristics X-ray, fluorescent X-ray and continuum X-ray. So, X-ray is also there. So, these are the different interaction behavior of the electrons with the sample component surface. So, if you just think of the scanning electron microscopic, you will get information about the near surface region of the component by detecting the secondary electrons. If you are interested to know about the deeper part of the object, you have to go for backscattered, you have to take the backscattered detector and just collect the backscattered electrons. And certainly the X-rays are also basically X-rays are usually detected with the help of energy dispersive in terms of energy or in terms of wavelength, with the help of energy dispersive spectroscopy or wavelength dispersive spectroscopy technique, and from there you get information about the composition. So, by scanning the surface with electron, you get lot of information. You get information about near surface topography, you get right at the near surface region the OJ electron is emitted. So, from the OJ electron detection you get information about the near surface just near surface composition. So, whoever people work on thin film technology, or whenever there is formation of very thin oxide layer on the surface, you have to go for OJ electron spectroscopy. If you are interested to know the detailed structure, little bit details, a kind of higher depth of penetration, you have to go for backscattered backscattered detector and then collect the backscattered electron. So, same scanning electron microscope, by just rastering the surface with electrons, you get lot of information. Now, if you just quickly go through the different types of scanning electron microscopy, their cost will also vary. Usually very simple scanning electron microscopy, they use typical that is tungsten as that filament. So, this is quite relatively cheaper, and a little bit higher version is that lab 6 detector, lab 6 that filament, and say if you just consider the highest among these categories, that is field emission tip, where the tip is basically created where the typical Schottky these things are defects are there, and also that cold these are all that high temperature that emission, but here thermal emission, but this is here it is cold emission. So, here you will have very sharp tip of the typical filament, and from there you will get electrons are emitted. So, the longevity of this particular filament is also highest. So, if you just quickly go through the comparison of different types of scanning electron microscopy, you will find that cost also will vary depending on the kind of filament and also the technology behind that. So, this particular, if you just check the tungsten filament, it is relatively cheaper, much cheaper than that of FE, that field emission current scanning electron microscopy. If you see the maximum current, that is basically maximum current required in FEG is lowest. So, you do not need much current for the emission of the electrons. Normalized brightness is much higher here, energy spread is much lower. So, energy spread is not required, because as energy is spread, naturally you will see that broader image, and it is very difficult to focal it in a very small spot. So, spot size is very high here, but it is very high in FEG. Required vacuum is much higher in field emission current scanning electron microscopy than normal scanning electron microscopy. Temperature is more or less not really, naturally this is cold phase, so it is having lower temperature. Lifetime, if you see, lifetime of the field emission gain is much higher than that of normal scanning electron microscopy. So, you can understand that different types of scanning electron microscopy is there, but whatever may be, basic principle is that as I mentioned you, that from the near surface region initially there is OJ electron, then secondary electron emission, and then gradually as you go on increasing the energy, naturally there is OJ electron, back scattered electron from deeper inside the material, there is back scattered electron emission. So, secondary electron is used for the determination of surface topography, near surface information, and back scattered electrons is having certainly higher depth of penetration. So, whenever you have the factography, or whenever you have that if you are interested to have the factographic information, you have to go for back scattered electron, or otherwise wherever you are interested to have very thick the details or very thick surface and you are interested to know the details about the deep inside the material, you can go for back scattered imaging. If you just compare the optical microscopy with scanning electron microscopy, you will find that in optical microscopy you use the typical visible light having wavelength from 2000 to 7000 angstrom. On the other hand, here broadly wavelength of 0.05 angstrom is used. The optical lenses are there for magnification. Here you use different types of lenses, that is electrostatic lenses. Magnification can be as high as 8 lakhs in scanning electron microscopy, even it can be as high as even higher than that, 10 lakhs is also possible. Here magnification is much lower, depth of focus is much higher here, higher here in scanning electron microscopy. Its resolution is much lower, on the other hand its resolution is quite high, and focusing by mechanical way, by electrical way, it is transmitted and reflected, it is naturally several, and contrast is color and brightness controlled, here shape and chemical property controlled. So, if you are interested to know about the surface features at a high magnification, you have to go for scanning electron microscopy, and if you would like to go for further details, you have to go for transmission electron microscopy. Now, another important parameter of the surface is the surface roughness. So, if you are interested to measure surface roughness, there are different techniques which are available, like depending on the magnification or depending on the finer features of the material, you can use any of the techniques, like you can go on doing optical or laser profilometer, wherever the surface roughness level requirement is of the order of, for example, 0.1 micron to maybe 1 millimeter. You can go for stylus profilometer, where finer details cannot be achieved by 0.1 micron. You can go for confocal microscopy, scanning tunneling microscopy, where finer details can be of the angstrom level, and atomic force microscopy, here again you can go up to sub nanometer level. So, depending on the required information or magnification or finer details on the surface, roughness of the surface, you can use any of the tool that is applied shown here. So, surface wafer roughness measurement, if you do by using contact tools, this is very easy technique, where you go on just moving a kind of stylus over the surface, and deflection of the stylus is noted down as a function of like position. So, from there you can get information about the surface roughness. In non-contact surface profilometer, you can use laser light or optical light. So, Here laser beam is used, it is rastered over the surface, and that deflection of the laser beam is basically detected or it is recorded as a function of position. In white light surface profilometer, you use white light which is scanned over the surface, and then you will find that typical it is basically you take that in one case you have the standard standard samples, and other case you have that your own specimen, and then typical interferometric principle you use for knowing the overall roughness level of the surface. In scanning tunneling microscopy, you keep the metallic tip very close to the conducting sample, and whenever they are very close, and if there is the typical voltage source, you will find that there is tunneling electron, the electron basically there is electron flow, and even there is a little distance, but electron goes on flowing, and that tunneling electron current is basically measured as a function of position. From there you get information exactly about the atomic structural, the kind of roughness which is created because of the presence of atoms and discontinuities thereafter. So, atomic force microscopy is again a kind of microscopy where which may be operated in contact mode as well as non-contact mode. So, you will find that in case of contact mode, you use that whenever two that probe and surface is very close to each other, then there is usually you will find that there is repulsive force, and then as you go on just increasing the distance, there is attractive force. So, you will find that at a particular if you just equilibrium make it kind of if you just go on having normalized these two values. So, the typical force which is applied on the at the in between region or between the two surfaces follows this kind of behavior, internal energy as a function of distance. So, basically this particular repulsive force applied for the contact mode operation, and that attractive force is applied for the non-contact mode operation. So, you have to know that there is a kind of cantilever which moves over the surface, and you can just check that particular typical that you can say that that position of the cantilever or maybe deflection of the cantilever is noted down. So, usually atomic force microscopy operates in 3 different modes: contact, non-contact mode, and also tapping mode, and you can get information about the finite details of the surface with the help of atomic force microscopy. So, you have to these all surface profilometers basically, and finally, if you can in a simple way, if you are interested to know the surface profile, you can go for typical laser profilometer or white light profilometer. If you are interested to know the composition of the this is very surface profilometer is very interesting technique for knowing the topographical features of the surface, and from the microscopy you get information about the specific microstructural features of the surface. If you are interested to know the composition of the surface, you have to go for energy dispersive spectroscopic analysis. As I said you that when electron beam interacts with the surface, naturally there is also X-ray generation. That X-ray energy may be detected by with the help of a detector, and you from that you can get information about the element which is present, or otherwise the wavelength of the X-ray may also be detected using the wavelength detector, wavelength dispersive spectroscopy, and subsequently you get information about the nature of the component which are present, and also components which are present or ingredients, or maybe you can say composition of the surface. If you are interested to know about the elemental composition, chemical state and electronic state of the component on the surface, you have to go for X-ray spectroscopic analysis. So, this is interesting technique where you just you just go on scanning the surface with X-ray, and then you measure the kinetic energy and number of electrons that are escaped from the surface from the near surface region. So, from there you get information about the composition, chemical state as well as electronic state of the matter, and this can also operate at very high voltage, very high vacuum. So, from there you can also get information about the typical binding energy of the component. X-ray diffraction technique is used for knowing the phases which are there on the surface. So, if it is for example, crystalline material, you get that typical peak, very sharp peak which satisfied the condition of the Bragg's constructive interference. So, from there these all peaks are from different planes, actually the constructive interference occurs from different planes. From there you get information about the lattice parameter, and you also get the information about the lattice strain from the broadening of the peak. There is, if there is a peak shift, that is usually because of the solid solution of one element into others, or otherwise it can also be because of the presence of the stress, residual stress. So, analyzing this, you get information about the residual stress, lattice strain, as well as the crystal structure, and also get information whether anything has gone in solution in case of alloy system. For the amorphous solids, this is a typical this hump you observe, and for monoatomic gas it is there is no diffraction peak which is observed, this is highly broadened. So, from the nature of the diffraction peak you get idea about the nature of the material, which is, or what are the what are the phases in the material. From the near surface region, if you are interested to know the spectroscopic analysis or maybe a composition of the near surface region, again you have to, with the help of a detector, you have to detect the near surface electrons which are emitted because of the scattering of the surface with electrons. So, another important parameter which is usually needed for knowing the wettability of the surface or energy of the surface, that is contact angle. So, contact angle measurement can be done by typical the sessile droplet testing, where you go on just dropping that water or whatever media where from you are interested to just do the contact angle measurement, and subsequently you find out that typical droplet shape, and using the Young's equation you find out the surface energy in different regions, either solid liquid or solid solid or liquid solid. And if you are interested to know the contact angle, that surface energy of unknown liquid, you have to go for doing two known liquid and one unknown liquid, and by using this Young's equation you can easily measure the contact angle or surface energy of the particular unknown liquid on the surface. So, these are important features or characteristics features which we discussed today. Particularly surface topography is very important, which basically controls many important properties like mechanical property like wear resistance, fatigue property, as well as corrosion resistance property. So, it is very important to know the typical surface roughness in a micro scale. So, which can be determined by surface profilometers, and if you are interested to know the very finer details of the surface, or maybe if you are interested to know the that is roughness at a very high magnification, you have to go for atomic force microscopy, or maybe you have to go for scanning tunneling tunneling microscopy. And if you are interested to know about that typical contact angle and then wettability of the surface, go for contact angle measurement. And finally, you have to correlate these all surface energy, surface roughness, microstructure and properties to know the mechanism of the interaction behavior of the component surface with the environment, and which gives very basic information. So, whoever are very much interested to know scientifically what is happening at the interaction point of the surface with the environment, they have to know these all things a little bit, so that you can establish good theory out of the behavior or out of the research work. And thank you very much. You are most welcome to ask any question through email, or maybe by just in the interaction session when we have in future. Thank you so much.